All right, welcome to today's Explainer. We are jumping right into a seriously fascinating piece of computer science engineering today, unpacking the core concepts of the memory hierarchy, locality, and performance. We're going to break down exactly how computers manage data storage to maximize both speed and capacity. Because, if you've ever wondered why your smartphone can snap open dozens of apps instantly, but still somehow has enough room for thousands of high-res photos, well, it all comes down to what we're about to talk about. So let's just dive right in.
Right off the bat, I want you to think about this incredibly fundamental engineering question. Why can't computers just have one giant, super fast memory chip? I mean, really, if we want our processors to be as fast as physically possible, why on earth do we bother with all these different types of drives and memory sticks? Why not just build the whole thing out of the absolute fastest material we have? It's kind of the central mystery of computer memory design.
And the answer? It basically comes down to the brutal reality of physics and economics. You are entirely forced into a trade-off. On one hand, you can have memory that is lightning fast, but it's going to be extremely small and wildly expensive per bit. Or, on the other hand, you can have massive capacity that is dirt cheap, but it's going to be incredibly slow to access. You just literally cannot have both in a single chip. It doesn't exist.
So here is our roadmap for today. 1. The computer memory dilemma. 2. The principle of locality. 3. The memory hierarchy pyramid. 4. Real-world architecture. And finally 5. The magic hit ratio.
Okay, starting us off with Section 1, the computer memory dilemma. How much, how fast?
Every computer architect basically loses sleep over 3 major constraints, which boil down to 3 simple questions: how much, how fast, and how expensive. Obviously, we always want more capacity, right? And we always want it to be fast enough so the processor never has to pause and wait for data. But practically speaking, the cost has to remain reasonable relative to the whole system. The designer's dilemma is that they desperately need cheap, high-capacity memory, but they also need fast, expensive memory to keep up with the processor. So how do we get massive, cheap capacity and blistering speed? Well, we kind of have to cheat.
Which brings us nicely to Section 2, the principle of locality. This is our behavioral workaround.
To really understand this workaround, let's imagine a guy named Bob working in an office. Now, Bob has thousands of folders stored in massive, really slow filing cabinets down the hall in the next room. But right on his desk, he has a small, fast file organizer that holds just a few dozen folders. Computer memory works exactly the same way. Instead of running to the next room for every single piece of paper, Bob clusters his work. Computers do this too. During execution, the memory references made by the processor naturally tend to cluster together.
And this clustering happens in 2 distinct ways. First up is temporal locality. This is simply the tendency of a program to reference in the near future exactly what it just referenced in the recent past. Think about Bob again. If he just read a specific folder, he keeps it right there on his desk organizer because logically, he's probably going to need it again very soon. Inside a computer, this exact behavior happens all the time during iterative loops or when it's using temporary variables.
The second behavior is called spatial locality. When Bob finally does have to go to that filing cabinet to grab a folder, he doesn't just grab the one he needs, he grabs the adjacent folders too, assuming his upcoming work is going to be related. In computers, if a processor references a specific memory address, it's highly likely it will need the addresses immediately surrounding it shortly after. This is especially true when a program is processing sequential instructions or moving through big tables of data.
So, now that we understand how data is actually used, let's look at Section 3, the memory hierarchy pyramid, the structural solution.
To actually solve this dilemma, engineers don't just pick one type of memory. Instead, they build this incredible hierarchy. At the very top, nestled right inside the CPU, you have tiny, unbelievably fast storage. But as you move down the pyramid, down through the cache, main memory, and solid-state drives, all the way to magnetic tape at the bottom, the capacity gets vastly larger, the cost per bit drops incredibly fast, but the speed gets noticeably sluggish.
The really crucial point here is that different hardware is handling these different levels. Up at the top, those CPU registers use incredibly complex, ultra-fast tech called CMOS, and they handle just a tiny 32-bit word. Think of it as a single syllable of data.
Then we step down a level to the cache, using SRAM or embedded DRAM, transferring slightly larger chunks of about 32 bytes. Keep going down to main memory. We're using cheaper, bulkier DRAM, moving whole kilobyte pages of data at a time. And at the very bottom, secondary memory, like magnetic disks, move entire 512-byte sectors. We are quite literally stitching completely different, highly specialized physical materials together to make this entire thing work.
But for this pyramid to function seamlessly without crashing, it relies on three strict design principles. First is locality, which we just discussed, keeping what's urgently needed close to the top. Second is inclusion. Let's bring Bob back for a second. Even if Bob has a folder sitting right on his desk, the mascot copy still lives securely in the filing cabinet. The computer copies data up the pyramid. It doesn't just move it. And third, coherence. If Bob makes notes on that folder on his desk, he has to make absolutely sure those updates eventually make it back to the master copy in the cabinet, so the whole system stays synchronized. If the processor alters data in the top cache, those changes absolutely must ripple down to update the lower levels.
All right, let's make this concrete in Section 4, Real-World Architecture, the IBM Z13 mainframe. Because this isn't just theory, right? Take the IBM Z13 mainframe computer, for example. This is exactly how a major enterprise system physically manages its data across multiple specific chips and processing cores. It takes all these abstract concepts and turns them into cold, hard silicon. Imagine this. Data rests in a massive 10 terabyte pool of main memory at the bottom. But then, through shared level 4 and level 3 caches, and then filtering into private level 2 and level 1 core caches, it gets relentlessly filtered. It keeps moving up until only the exact bits needed this very millisecond hit the processor. It's a beautifully orchestrated funnel, perfectly sorting data based purely on immediate need.
But how do we actually know if this incredibly complex funnel is working? Well, that brings us to Section 5, the magic hit ratio, measuring success.
90%, or a 0.9 hit ratio. This right here is the magic number. Because that fast on-chip cache is anywhere from 25 to 50 times faster than the main memory, the processor absolutely must find the data it's looking for in that fast cache about 90% of the time. If it doesn't, it has to completely pause and wait for the slow main memory to fetch it, which is terrible for performance.
Put simply, for every 10 pieces of data the processor asks for, 9 of them must already be waiting in the lightning-fast top layers of our pyramid. Because if that misslice gets too large, the mathematical average access time of the entire system plummets. It drops closer and closer to the speed of the slow, cheap memory. If that happens, the whole illusion just completely breaks down.
And that is exactly what this whole setup is, a brilliant, clever engineering illusion. By deeply understanding human and programmatic behaviors like temporal and spatial locality, engineers take a bunch of cheap, really slow drives, layer a tiny amount of ridiculously expensive fast memory on top, and effectively trick the processor into acting as if it has an infinite amount of instant storage.
Which leaves us with a pretty fascinating question to ponder. We've gone all the way from old-school mainframes to modern smartphones using this exact same principle. But as our global datasets explode into the zettabytes with AI and massive global networking, what is the next level of this memory pyramid going to have to look like to keep this illusion alive? Thank you so much for joining me for this explainer. I hope this really clarified the brilliant architecture that's powering our digital world.